we'll continue our learning series during this quarantine period. And today's topic is gravity. So first of all, what is gravity? In the most basic terms, gravity is the force by which the earth pulls everything towards it. So, for example, if an apple, the famous example, if an apple falls from a tree, it doesn't fly in the sky, it actually falls down towards the earth. But actually, it's not just that. Now, let me ask you a basic question. What happens when something is dropped? And this is a very simple question. The answer is things fall down towards the earth. And people have been fascinated by this simple question. So Aristotle was among the people who pondered over this question, and he said, for example, if you have a ball made of iron and it weighs 10 kilograms, and yet there's another ball made of iron but it weighs only 5 kilograms, if you drop them from the same height, they will fall at different speeds. And people believed in this for a long time. Now enters our next hero of the story of gravity, and his name is Galileo Galilei. The year is 1583. Galileo is 19 years old and he lives in this city of Pisa. Galileo is supposed to listen to the sermons, so there's a lot of chandeliers on the ceilings to give light to people who are gathered to listen to the sermons. But Galileo has no interest in the sermons. Instead, he just starts looking up and he starts noticing, well, there are big chandeliers and small chandeliers, all different sizes of chandeliers are just spread across the ceiling. So he starts measuring the pendulum movement of these chandeliers. Today, we take things like watches as granted, but in Galileo's time, you'll be surprised to know that such a great scientist didn't have a reliable way of measuring time. So he uses his pulse to time the pendulum movement of chandeliers. And to his surprise, he discovered that the time it takes for the pendulum to complete one cycle does not depend on the weight of the chandelier, but it actually depends on the length of the rope or the string by which it is hung to the ceiling. And that was an eye-opener for young Galileo, because this challenges Aristotle's idea. People had been believing Aristotle's theory. To Galileo's surprise, mass doesn't matter. So what does he do? And so he then took the leap in his reasoning and said, I can then deduce that when things are in free fall, then also it doesn't matter what the weight of the free falling things are, as long as they are dropped from the same height, they should reach the ground at the same time. And so in 1589, Galileo is about 25 years old. He does this famous experiment. He drops balls of different weights from the top of the Tower of Pisa, and he does a public display of his discovery that actually weight doesn't matter. Galileo then reasoned, if you take away the air, if you create a vacuum, and then if you drop a feather and ball of iron, they will fall to the ground at the same time. They'll take the same time to reach the ground. So Galileo was interested in knowing whether the speed of a falling thing remains the same as it reaches the ground, or does it increase, or does it decrease? He didn't know. So what he did is he had a slope, and from the top of the slope he would drop a ball, and then he would time the ball. How much distance does it travel in how much time? He finds that as the ball keeps on rolling, the speed increases. He figures out that in the first second, the ball rolls, let's say, 1 meter. After 2 seconds, the ball has covered a distance of 4 meters. After 3 seconds, the ball has covered a distance of 9 meters. After 4 seconds, the ball has covered a distance of 16 meters. After 5 seconds, the ball has covered a distance of 25 meters. Now, can you see the correlation here? This law that Galileo discovered is called the time-square law, which means the distance traveled by a ball on a slope can be measured as t square. And mind you, Galileo did these experiments and he deduced this time-square law and the law of pendulum when there were no reliable sources of measuring time. The system of equations in mathematics had not evolved. The notations of mathematics had not come about. People didn't use mathematics the way we use. So he was still using the old mathematics rules of finding the ratios and proportions. But for the first time, Galileo discovered acceleration. So he reasoned, if you just make the slope higher and higher, more and more towards the vertical line, it will still keep the relationship of acceleration. So he said, yes, as things fall down, they accelerate. So this idea of things gaining speed, accelerating, was verified by Galileo. But that's all Galileo could contribute to our story of gravity. And now let's move on to the next hero of our story of gravity, and that is Sir Isaac Newton. So the year is 1665. Newton, 22 years old, is studying at the University of Cambridge. And in the nearby city of London, the infamous bubonic plague raises its ugly head. The scare is so much that the University of Cambridge decides to close the university, and all students were then asked to go back to their homes until further notice. So Newton starts a journey to his home about 100 kilometers away. There, he is quarantined for 18 months. And in that solitude of his quarantine period of 18 months is when he discovers the law of gravitation. So, just like today, we have COVID-19, people have been living in quarantine for 3-4 months now. Well, if you use your quarantine properly, like Newton did, maybe you can end up discovering a new theory of quantum gravity. Who knows? What is the law of gravity? Well, he summarized everything with a very simple equation, which is this. This is a very simple equation. M1 and M2 are the weights or the masses of things that we are considering gravitation between, and r is the distance between them. And so Newton says this is the relationship and there must be a gravitational constant. And Newton doesn't know the value of that gravitational constant at that time, but he says, well, there must be. We have to find this gravitational constant, and once we find, we can actually find the gravitational force between two things. Now that's super amazing, a simple equation. And people work on the equation and they find that actually Newton's laws work perfectly on things that, for example, fall towards the earth. Newton's genius was thinking, okay, so apples fall to the ground because earth attracts them with the force, and he named the force gravity. So according to Newton, gravity is a force. Now, keep this in your mind. So when things fall down, they fall down because earth is attracting them towards itself with the force of gravity. And then Newton looked up in the sky and he thought, wait a second, so what about the moon? Isn't it possible that maybe the earth also attracts the moon around it, keeps it in the orbit because of its gravitational pull? And that was the leap. And by the way, that's also the reason why Earth moves around the Sun. The Sun attracts Earth with its gravity. Not only Earth, but also attracts other planets that we knew at that time. And then people made calculations and they found, yes, that's true. But very soon, people started finding the problems with Newton's equation. It's a simple equation, and it's true for most things that we observe in our everyday life. And of course, for moon and sun and the Earth's rotation around the sun, things work very well with this simple equation. But some scientists, some people also found that this equation is good for a set standard, a minimum and a maximum weight of things. But beyond it, it doesn't work very well. So there were two problems with Newton's idea of gravity as a force. First, when people asked Newton, how does the moon stay around the earth? Newton says, well, just take a stone and tie a string around it and move it around you. What happens? What happens is, because of this movement, the stone wants to go away, but it doesn't go away because the string keeps the stone in balance, moving it in the air, so it doesn't go away. Similarly, gravity is like a string. It's an invisible string. I can't find it, but maybe in the future people will find this string. But people said, well, that's like you're talking about voodoo, an invisible string that keeps things in balance in the universe. When people asked more, Newton just said, well, these are the things that are created by a superpower. Because in Newton's time, even scientists believed in God, and he also believed in alchemy. But anyway, despite these shortcomings, he was a legitimate genius of his time. So that's the first problem with this theory of gravity offered by Newton, because there's no string. The second problem was when people measured motion of different planets around the sun, they discovered that, yes, of course, Earth's motion and Venus and Mars is defined very well by Newton's equation. But Mercury, the nearest planet to sun, it deviates from the path predicted by Newton, so it doesn't follow Newton's equation. Also, a new planet was found called Uranus, and Uranus also doesn't follow the path that is predicted by Newton's equation. So Newton's law of gravity works, but for a narrow spectrum of things. It works for things that are at a certain distance from the sun and up to a certain distance in the solar system. There were limits to how far we can use this equation. So for things that are very near to the sun or that are very far away from the sun, this equation didn't work very well. Now enters our next hero in this story of gravity, and his name is Albert Einstein. Let's now move to 1915, the year Albert Einstein devised the theory of general relativity. But the work already started. He's already started thinking about it in 1907 when he was working at a patent office. One day, he saw a painter who was painting the walls of a neighboring building. Some accident happened and he started falling down towards the earth. And Einstein started thinking about it. What does gravity have to do with a falling person? Well, according to Newton, gravity is the force that is pulling the person down towards the ground. But Einstein thought, imagine you are riding a roller coaster and you're going up and then you start falling down. When you are falling down, you feel very lightheaded. You feel as if you will fly in the air. You feel weightless. Similarly, experiments have been done with people on elevators. So if you're standing on a weighing machine inside an elevator, and let's imagine the elevator starts accelerating towards the earth, you will observe that the weight, your weight, actually decreases. If you accelerate to the ground in an elevator at 9.8 meter per second square, actually the weighing machine will show your weight as 0 kilograms. Isn't that interesting? Now, if that painter starts falling towards the ground, does he feel his weight? He doesn't feel his weight. His weight is 0. When something is in free fall, it doesn't have any weight. It has 0 weight. It's as if you're falling in space. So Einstein said a person floating in the space is the same as a person falling down from a building. Both of them have 0 weight. So both of them have an equivalence, and that principle is called the principle of equivalence. Now, why is that important? Because Newton's idea of thinking of gravity as a force doesn't hold much weight. So, if gravity is not a force, then what is it? And then Einstein comes with a new explanation of gravity. The speed of light remains constant, and using the speed of light, he proves that time and space are expandable. Space can expand or contract. Similarly, time can expand and contract. And so he proposed this idea of space-time fabric. What is space-time? Well, space we understand. We have three-dimensional space. But Einstein said space and time are interwoven into each other. Imagine a fabric made of elastic rubber. Now that is space-time. So space is the three-dimensional space that you have, and time is interwoven into this fabric of space. And so Einstein proposes that a massive object like Earth, when it falls on that space-time fabric, it actually bends the fabric of space-time. And when it bends the fabric of space-time, it actually creates curves in the space-time. Sun is much more massive than Earth, so it warps the fabric of space-time with a greater curve. When Earth creates the warp in the space-time, the moon, for example, revolves around it, not because of the gravitational force, but rather because Earth has warped the space-time. So the moon is revolving just because of the warping of space-time due to Earth. Similarly, we feel that the Earth is revolving around the sun, but in reality, the sun keeps on moving and the Earth keeps on falling down the space-time curvature created by the sun. So Einstein's idea of space-time actually expanded our understanding. And after it was discovered by Hubble that our space, our universe is expanding, actually Einstein's equations predicted many more things which actually have proven to be true. For example, Einstein's equations predicted gravitational waves. In September of 2015, for the first time, we were able to measure gravitational waves which were generated 14 billion years ago by two neutron star massive things revolving each other and smashing into each other. I think it was September 14th, 2015. On that day, our Earth actually warped a little, a teeny tiny amount, but it did press a little. That is super amazing. Einstein also predicts black holes, which now astrophysicists have actually observed in the space. Einstein also applied his equations on the path of Mercury. Now remember, if you apply Newton's equations, you cannot define with accuracy the path of Mercury and Uranus. But if you use Einstein's equations, yes, Einstein's equations are applicable on everything you can measure with Newton's equation, but they go beyond Newton's equation. If you apply Einstein's equations on Mercury and Uranus, you can actually predict their path around the sun with much more accuracy. So now the idea of gravity, because of space-time, actually has many more things than just the planets around the sun. So gravity is not a force, but rather it's a field. What is a field? A field is just like a matrix that's interwoven all around you. And it's when a massive thing like Earth interacts with space-time, it warps. And that curving of the space-time, warping of the space-time creates gravity. So what we call gravity is nothing but warping of space-time. So gravity is a field, it's not a force. And that is a big, massive leap. So we are coming all the way from Aristotle thousands of years ago, saying that, yeah, things just fall down to the ground and their speed depends on their mass. Galileo and Newton proved that that's not true, and Einstein proved that actually it's not a force. Gravity is not a force, it's a field. It's a matrix which interacts with massive objects, things with mass. But Einstein's space-time idea of gravity has also its own limitations. First of all, it doesn't define massive black holes. So first, let's talk about what a black hole is. What happens when a star dies? And let's say the star is as massive as Sun. When a star dies, it enters into different phases. Finally, it reaches the stage of a neutron star. What is a neutron star? A neutron star has the same weight as, let's say, our Sun, but the diameter of neutron star is around 20 kilometers. And when this thing interacts with the fabric of space-time, it actually makes a very big warp into it. And that's what a neutron star does. A neutron star creates a huge warp because of its extremely high mass, but limited space. So the space-time that it interacts with has a very small horizon. So that's what neutron stars do. Now, what is a black hole? A black hole is a neutron star's big brother. What do you mean by that? A black hole is, first of all, it's not a thing. Like, for example, a neutron star is a neutron star, Sun is Sun, but a black hole is not a thing, it's a place where things happen. So imagine the weight of sun, but in the dimensions of a small marble ball. So now when this kind of thing interacts with space-time, it makes such a huge warp into it that the space-time breaks in those places. So in a black hole, the idea of space-time doesn't exist any longer. So Einstein's equation don't hold in a black hole. That's the upper limitation of Einstein's space-time equations. Now there's also a lower limit, and that is quantum mechanics. At the smallest of the smallest level, small particles, they don't follow Einstein's space-time equations. A proton or neutron or electron, they have some mass. So as long as you have mass, you should be able to interact with the space-time around you. But they don't follow Einstein's space-time equations. They don't warp the space-time as they should, as predicted by Einstein's equations. So very small things work on the mechanism of quantum mechanics. Quantum mechanics doesn't follow Einstein's space-time equations. So, what is gravity? We started with gravity as simply a force. Then we said, well, gravity is not just a force, it's a field. But even that breaks down at very small, at subatomic level, and at very big, at black hole level. Einstein's equations don't hold. So today scientists are trying to find what you can call quantum gravity, wherein everything from subatomic to the black hole and beyond that is defined by a single equation. Scientists today are trying to find the common ground between quantum mechanics and Einstein's field equations, and when these things match, that would be a uniform theory of gravity. So that was our video for today. Thank you for watching, and as always, please like, subscribe, and spread this video as much as possible. And I'll see you in the next one. Until then, bye bye.